Okay, hi everybody. So today we're going to go over some double integrals and polar coordinates, okay? So first we need a couple of definitions. So the first one we're going to deal with is a simple polar region, okay? So a simple polar region in a polar coordinate system is a region that is enclosed between two rays theta is equal to alpha and theta is equal to beta, and two continuous polar curves R1, which is equal to R1 of theta, and R2, which is equal to R2 of theta. Where, and we have some conditions that we have to satisfy here. Okay, 1, alpha is going to be less than or equal to beta. 2, beta minus alpha is less than or equal to 2 pi. And 3, R1 is going to be less than or equal to R2, and they're both positive. Okay, so why is that the case? Okay, so what we have here, and I know this is not the XY plane, but I'm putting them in there just because it gives you some reference of what's going on. Okay, so what we do is we have a ray here, and I'm going to call this alpha, and this is another ray right here, and this is beta. And then therefore this angle between it is beta minus alpha. Okay. Well, why these conditions? It's basically just to make things work out nicely, right? If you have a situation where alpha and beta, they like flip-flop, well, might be negative or positive, the difference between the two. Why is it this way? Beta minus alpha is less than or equal to 2 pi. Because this angle has to be less than 2 pi. If it's bigger than 2 pi, it's going to rotate back on top of itself. So we have to leave that alone. And then just for convenience sake, we're going to say R1 is less than or equal to R2. So here's maybe R1, and then R2, maybe something like this. And this is R1 of theta. So the simple polar region that I have here is going to be this. Okay, that's what I'm looking for. Okay, so what is a polar rectangle? Let's go further and let's define this, okay? So polar rectangle is a simple polar region. So what we've defined up above, for which the bounding polar curves are circular arcs. Okay, so what does that mean? Okay, you have the same type of a graph. Okay, you have two angles here and there. Once again, that's alpha, and from there to there is beta. Okay, so a polar rectangle is when you have an arc here, that's a circular arc, and another circular arc right there. And so right here, that is what's called a polar rectangle. Okay? Now, what do we do with these? Okay, so this is exactly what we did last time with these. Okay, we're going to take a region R, which is going to be on some sort of a plane, and we're going to take that, we're going to project it up to the third dimension. So we're going to evaluate it for some Z, which is going to be f of R theta. Okay, so we have to be careful here, and this is where we're going to get into our artistic ability. Okay, so I have some sort of a three-dimensional graph. Once again, I know that this is not a polar plane, but I'm putting it on there so you guys understand what it looks like. Okay, so this is my Z. And what I have is I have some sort of an angle right here that comes out, and this is going to be alpha. And I have some sort of another angle that comes out here. So from there to there is alpha. And then you have another angle that goes from there to there, which is going to be beta. And then you have some sort of a curve that goes through here, which is maybe going to be my R1. And some sort of a curve right there that's going to be the R2. And then what I'm going to do is I'm going to break this simple polar region into a whole bunch of different polar rectangles. Okay, so I'm going to draw in these nice circular arcs. Nice circular arcs. Nice circular arcs. Okay, and then I'm going to put out a bunch of rays here. So this ray, that ray, and so on. Should be thinking Spider-Man right now. Okay, now what we're going to do is we're going to focus in on one of these. Okay, we're going to focus in on what we're going to call the kth rectangle. So that's going to be this one right here. And inside of there, we're going to put some arbitrary point. And the arbitrary point is going to be R, K, star, theta, K, star. Okay, the star represents that it's an arbitrary point inside of that. Okay. Now, what's going on here? Remember, so this is the region R, which is our domain, and we're going to take this and we're going to project it to some function f. And so it's going to be like going to the third dimension. So I'm going to pretend on top of here, there's some sort of like canopy. So it might go like something like this. Okay, and it goes there, and it goes there. Okay, so this is going to be the curve, whatever f of r theta is. What we're going to do is we're going to find the volume of this underneath this curve. And we're going to do this by projecting, by making a whole bunch of these parallelepipeds. I know there's a whole lot of lines going on here. Okay, and so what we're going to do is we're going to find the volume of that one parallelepiped, but then we have a whole bunch of them, right? So what are we going to do? We're going to add them all up, just like we always do. And once again, that's just going to be an approximation of what the actual volume is. So all we have to do is we have to continue to make more and more and more and more of these. Okay? So what we're going to do is we're going to sum these up. And we're going to let k go from 1 to n of whatever f of r k star theta k star is. And then we're going to multiply it by some delta A. Delta A is going to stand for whatever is the area of this polar rectangle. Okay, so this is the area of the polar rectangle. And this is going to represent the height of some arbitrary point inside these. And we just want to add them up. But once again, that's just going to be approximation. So what we do is we have to take the limit of this, and we're going to take the limit as n goes to infinity of this function. And when we do this, this is going to give us what the actual volume is. Okay? And I should list out a little bit more here. Okay, where r k star theta k star is an arbitrary point in the kth polar region and delta A is the area of that polar region. Okay, so what we have there then is when we take the limit of this, we're going to write this as the double integral over the region R of f of r theta dA. And like I said, this is actually the limit as n goes to infinity of the summation as k goes from 1 to n of f of r k star theta k star delta A. Okay. So, what do we do now? Okay, so evaluating this. Okay, so how do we actually evaluate this? How do I find out what the limits are going to be? Okay, so this right here, if R is a simple polar region whose boundaries are the rays, theta is equal to alpha, and theta is equal to beta, and the curves R is equal to R1 of theta, and R2 is equal to R2 of theta, and if f of r theta is continuous, then we have the double integral over the region R of f of r theta dA is equal to the double integral over the region R of f of r theta r dr d theta. Now, where in the world did this r come from? I'm not going to go through a whole big explanation. I did this in class a little bit, but it all has to do with the formula for finding the area of a polar region, right? So if we take a look at what dA is, dA actually comes from delta A, and delta A we could say is equal to 1/2. So if you remember what the formula for the area of a polar region is, the area is equal to 1/2 r squared d theta. And if we use that formula, then delta A is equal to 1/2 r k star plus 1/2 delta r k squared, and then minus 1/2 r k star minus 1/2 delta r k squared. I know that's a lot, and you probably don't understand exactly what that comes from, but it does come from something like this. So if you have a polar region like this, and this point right here, I'm going to put directly in the middle, and that's going to be my r k star theta k star. And if this distance right here is my delta r k, then that distance is 1/2 of delta rk. Okay, I'm going to leave it at that. I'm going to let you guys figure that out. There's a lot of piecing it together there, but I put together some pieces of the puzzle there for you. Okay? Okay, so let's go to the example.
I'll go to the post office.
Okay, so the example we have here is we have the double integral of sine of theta dA, where r is the region in the first quadrant, that is outside the circle, r is equal to 2. And inside the cardioid, r is equal to 2 times 1 plus cosine of theta. Now, I didn't set up a whole lot of room here, and it's my fault. I accidentally put this on this page and not the other page. So I'll probably just do a little bit of the setup of it, and then let you actually evaluate the integral on yourself or by yourself. Okay, so the first thing I need to know is I need to know what the region R is. And that is like the most important things when we're evaluating things in multivariable calculus. Okay, so if you look at the region R, it says that it's outside the circle, R is equal to 2. So that's this circle right here. Okay, we're only in the first quadrant. And then it's inside the cardioid of 2 times 1 plus cosine of theta. Well, that looks like this. Okay, and if you don't understand why, if you plugged in theta is equal to 0, then that would be 1. 1 plus 1 is 2. 2 times 2 gives you 4. And then this is pi over 2. And if you plugged in pi over 2 for this, cosine of pi over 2 is 0. 0 plus 1 is 1. 2 times 1 gives you 2. So this is the region R, which I want. So then this integral up here becomes sine of theta r dr d theta. And now I need to know what my r's are going to go from what to what. So my r, the smaller portion of it, is just going to be 2. No matter where it goes, it's always going to be 2. And then the bigger radius is going to go all the way out to the outside one, which is the equation 2 times 1 plus cosine of theta. So 2 times 1 plus cosine of theta. And then what are my thetas going to go from what to what? So the smallest my theta is going to be is right here is 0, and it gets rotated all the way up there to pi over 2. So it goes from 0 to pi over 2. Okay. Now, like I said, I'm going to let you evaluate this. But it turns out that when you do this, it's going to give you a value of 8/3. Okay. You have to go back to your Calc BC days to figure out that one. Okay. I will tell you it involves a couple of things here. But most importantly, it's just going to be U substitution. Okay. Okay. Example 3.3.2. Okay, the sphere of a radius A centered in the origin is expressed as a rectangular coordinates using x squared plus y squared plus x squared is equal to a squared. And hence its equation is in cylindrical coordinates is r squared is equal to plus z squared is equal to a squared. We'll talk further later on about what exactly is cylindrical coordinates. Now, the goal of this question is actually to derive the formula for the volume of a sphere, and the volume of a sphere is 4/3 pi r cubed. But in this instance, my radius A, so I'm trying to find 4/3 pi a cubed. That's what I want to show. Okay, so let's get after this. So what I have is I have a sphere that's centered at the origin. So okay, so that's the intersection down there. And then it's going to come up here. Whoa. And then go down below. Okay, so I guess it looks just something like that. Okay, that is a really awful sphere. I'm sorry about that. Okay, so what I'm going to do is I'm going to find the volume by using the double integral of f of r theta r dr d theta. Now, I have to determine what my r region is going to be. Well, the r region is going to be if you come over here and you were to like squish this, right? If you squish it down on the xy plane or on the polar plane, it's just simply going to make a circle. Okay, where the radius here is a, and you're going to rotate it through 2 pi radians. So all this is going to end up being is the integral of, and we have to let this go for a moment. We'll figure out what that is in a second. And then I have r dr d theta. And my r values are just going to simply go from 0 to a. And my theta is going to go from 0 to 2 pi. Now, what is my function here? Okay, so my function is given by this equation right here. And if you solve for z here, you have z is equal to plus or minus the square root of a squared minus r squared. Now, what I'm going to do is I'm only going to integrate the top portion of it. And then I'm going to double it. Okay? If I integrated just the top portion of it, I would just figure out what the top volume is going to be. But I need to know what the bottom volume is going to be as well. So I double it. Okay. So here, this is just u substitution. The derivative of r squared is going to give you the r right there. So this is going to be 2 times the integral from 0 to 2 pi times a minus r squared to the 3/2 power divided by 3/2, which is going to give me 2/3. But remember, I needed to divide through by the derivative here, which is negative 2r. So the r's will cancel, and so I still have to divide through by negative 2. And then I have to evaluate this from 0 to a d theta. So this 2 will cancel this 2. I bring out the 2/3. I'm going to integrate from 0 to 2 pi. And I'm just left with a minus r squared to the 3/2 power. I'm going from 0 to a d theta. Okay, so this is 2/3 times the integral from 0 to 2 pi. Okay, let's evaluate this. So you plug in a, you're going to get 0. This should be an a squared. This is a squared. This is a squared. So you plug in a, you're going to get 0. So you plug in 0, that's going to go away. You have a squared to the 3/2 power. Well, that's just a cubed d theta. And you can see it start to developing. There's the a cubed. So this is equal then to 2/3. Now this is a. This is just a constant with respect to theta. So this is just a cubed theta from 0 to 2 pi. So this is going to give you 4/3 pi a cubed, which is what I wanted to show. Okay. 3.3.4. Okay, the volume, this is so weird, the area of a polar region. So the area of a region R in the xy plane can be expressed as the double integral over the region R of 1 dA, which is just equal to the double integral over the region R dA. Now, this is stupid. Why write it this way? So we write it this way because it like compacts everything. If you think about the other way that you'd normally write it, you'd write it as the integral from a or from alpha to beta of 1/2 r squared d theta. While this is fine and it probably takes up just as much ink as what this does, this is more compact. Okay, you get rid of the numbers and you just have a few symbols there. Okay? So let's go ahead and use this. Use a polar double integral to find the area enclosed by 3 petaled rows. R is equal to sine of 3 theta. So that rows looks like this. Okay, so we want to find the area of those. So all I'm going to do is I'm going to find the area of one of them, and I'm just going to triple it. So this is going to be 3 times the double integral over the region R of dA. Now, I need to figure out what my what my limits of integration are going to be. So this would be 3 times the double integral of 1 r dr d theta. And then my r, the smallest is going to be a 0, and then it's going to go out to whatever that curve is, which is sine of 3 theta. So I'm going to go 0 to sine of 3 theta. And then the angle measurement, I need to know what that angle is, and I need to know what that angle is. So if you remember the trick in polar, is you set this equal to 0 and you solve. So you go 0 is equal to sine of 3 theta. Take the inverse sine of both sides. So you have 3 theta is equal to 0, because that's where it's equal to 0 at. This is a 0. Sorry, not a theta. So theta is equal to 0, but you also have 3 theta is equal to pi. Okay, because it's also equal to 0 at pi. So theta is equal to pi all over 3. So this angle is actually 0, and this one is pi over 3. So I'm going to integrate from 0 to pi over 3. Okay, now I'm going to let you guys do this. This will require having to know what the integral of sine squared is. Okay, so I've done the setup for you. And when you do this, it just turns out that it's equal to pi all over 4. Okay, once again, that's an integral you should be able to evaluate going back to Calc BC. Okay, and then one more. Use the polar coordinates to evaluate this thing. Now this looks like an awful mess. Okay, but what's really nice here is when we switch it to polar, it's not so bad. So remember, there's a key here that switches from parametric to polar, and that equation is x is equal to r times cosine theta, and y is equal to r times sine of theta. So if you look at x squared plus y squared is equal to r squared cosine squared theta plus r squared sine squared theta, which is equal to r squared times cosine squared theta plus sine squared theta, and that's your baby. That's 1. So that's just r squared. So this is the integral from -1 to 1 of 0. Oh, I'm not going to do those limits. Sorry, I'm going to switch those limits. So this is the integral, the double integral. This is going to be r squared, because that's what we found it to be, to the 3/2 power, and then r dr. What am I doing? R dr d theta. Okay, now what about my limits? What are my limits going to be? In order to do my limits, I need to know what this region R is going to be. So my y values are going to go from 0 to there. So my y values are going to go from y is equal to 0 to y is equal to the square root of 1 minus x squared. If you square both sides and rearrange that, you get this equation x squared plus y squared is equal to 1. So that's just a circle, but it's only going from 0 to there. So what it's really talking about is it's talking about a semicircle up here on the top. Now, what about my x's? My x's are going to go from -1 to 1. Well, there's -1 to 1. So this is the region R that I'm talking about. So what is my R going to go from? It's simply going to go from 0 to 1, because that's what the radius is. And then the theta measurement is going to go from 0 to pi. Okay, so this square is going to cancel that. That's going to be r cubed times r gives you r to the 4th. The integral of r to the 4th is r to the 5th over 5. So this is the integral from 0 to pi of r to the 5th all over 5 d theta. This is going from 0 to 1. So this is the integral from 0 to pi of 1/5 d theta, which is just going to give me pi all over 5. Okay, so this really complicated integral up here, when you switch it to polar, makes it really nice and easy. Okay, so there we are. the section 3.3 graphing using polar regions. If you have any questions, please feel free to reach out to me. Thanks, everybody.